Hello friends. I am here to discuss topic, batch, and continuous sterilization process. Part of NMEICV project, entitled Creation of E-Contents on Fermentation Technology. Sponsored by the MHRD Government of India. Medium sterilization. Medium sterilization is chief phase of the fermentation processes. Proper sterilization of media is essential for successful fermentation processes. Media sterilized by 1. Filtration, 2. Radiation, 3. Ultrasonic treatment, 4. Chemical treatment, 5. Heat. Out of these methods, heat or steam is the most useful method for the sterilization of fermentation media. Number of factors influence the success of heat sterilization. 1. The number and types of microorganisms present. 2. The composition of the culture medium. 3. The pH value and the size of the suspended particle. Filtration used for the sterilization of medium, which is exception for the medium containing heat-labeled components. Sterilization process that is killing of microbes by steam under pressure is a first-order chemical reaction and, thus, may be written as -dN/dt equals Kn equation 1, where N is the number of viable organisms present, T is sterilization treatment time, K is the reaction rate constant of the reaction, or the specific death rate. Regardless of the volume of the batch, the minimum number of organisms to contaminate the batch is 1. On integration of equation 1, the following expression is obtained: Nt/N0 equals e raised to minus kt, equation 2, where N0 is the number of viable organisms present initially, Nt is the number of viable organisms present after a period treatment T, on taking natural logarithms, equation 2 reduced to natural logarithm n, T/N0 equals minus k, T, equation 3. Therefore, k, T equals natural logarithm, then, 0/n, T. Equation 4. Graphical representations of equations 2 and equation 3, illustrated in figure 5.1, a plot of the natural logarithm of Nt/N0 against time, yields a straight line, the slope of which equals minus k. This kinetic description makes two predictions, which appear abnormal. 1. Sterile condition is achieved in an infinite time, that is, Nt equals 0. 2. After a definite time, number of cells present will be less than 1. The relationship displayed in figure 5.1, observed only for pure culture in certain metabolic state, under ideal sterilization conditions. The value of K also indicates physiological state of organisms with kind of species, but dependent on the physiological form of the cell. For example, the endospores of the genus Bacillus are far more heat-resistant than the vegetative cells. Richards 1968 produced various graphs illustrating the deviation from theory, which experienced in practice. Figure 5.2 shows the relation between bacterial endospore survivals versus time of treatment. The deviation in the above graph is due to the induction of spore germination by the heat and moisture of the initial period of the sterilization process. Figure 5.28, early stages provide temperature for the growth of the spores, hence the number of viable cells increases in the initial stage, and then there is killing of spores at the later stage. In figure 5.2b, activation balanced by spore death, and in figure 5.2c, activation is less than spore death. Medium sterilization. Medium sterilization is chief phase of the fermentation processes. Proper sterilization of media is essential for in figure 5.38, the population consists mainly of the less resistant type, where the initial decline is due principally to the destruction of the less resistant cell population, and the later, less rapid decline is due principally to the destruction of the more resistant cell population. Figure 5.3b represents the reverse situation, where the more resistant type predominates, and its presence disguises the decrease in the number of the less resistant type. Number of factors influence the success of heat sterilization. 1. The number and types of microorganisms present. 2. The composition of the culture medium. 3. The pH value and the size of the suspended particle. Filtration used for the sterilization of medium, which is exception for the medium containing heat-labeled components. Sterilization process, that is killing of microbes by steam under pressure, is a first-order chemical reaction and, thus, may be written as -dN/dt equals Kn equation 1, where N is the number of viable organisms present, T is sterilization treat as first-order reaction. As temperature increases, reaction rate increases, due to an increase in the reaction rate constant, which, in case of the destruction of microorganisms, is the specific death rate K. Thus, K is true constant, only under constant temperature conditions. The relationship between temperature and reaction rate constant was demonstrated by Arhenius, and may be represented by the equation. Derivation of natural logarithm of K/T equals E/RT square, where E is activation energy, R is gas constant, T is absolute temperature. On integration, K equals A into E raised to minus C/R T. Therefore, K T equals A into T into E raised to minus C/RT. On taking natural logarithm K equals natural logarithm A minus E/RT. Plot of natural logarithm K versus 1 upon T gives straight line. Such a plot is Arhenius plot, and enable calculation of activation energy, and prediction of the reaction rate for any temperature. Now natural logarithm N T/N 0 equals minus KT. So, natural logarithm N 0/N T equals KT. Therefore, natural logarithm N 0/N T equals A T E raised to minus C/RT. The Vidya-mitra and Humphrey, 1959, used the term natural logarithm N 0/NT as a design criterion for sterilization, which has been variously called the Dell factor, Miller factor, and sterilization criterion represented by the term Dell. Thus, the Dell factor gives idea about fractional reduction in viable organism count produced by the definite heat in particular time. Now Dell factor equals natural logarithm N 0/N T, but from above equation natural logarithm N 0/N T equals A T E raised to minus C/RT. Thus, Dell factor equals A T E raised to minus C/RT. On rearranging equation, natural logarithm T equals E/RT plus natural logarithm Dell factor/A. The graph obtained from this equation, used to obtain definite Dell value, with certain absolute temperature. If we plot the graph from above line equation, then we will get idea about time and absolute temperature required to achieve sterilization. According to the Vidya-mitra and Humphrey, Richards, Banks, and Corbett, risk factor of one batch in 1,000 contaminated, frequently used in fermentation industries, that is, the final microbial count in the medium after sterilization, should be 10 raised to minus 3 viable cells. To apply kinetics, it is necessary to know the thermal death characteristics of all the taxa contaminating the fermenter and unsterile medium. This is an impossible, and therefore, the assumption may be made that the only microbial contaminants present are spores of Bacillus stenotyphophilus, that is, one of the most heat-resistant microbial types known. Thus, by adopting Bacillus stenotyphophilus as the design organism, a considerable safety factor built into the calculations. It should be remembered that Bacillus stenotyphophilus is not always adopted as the design organism. If the most heat-resistant organism contaminating the medium ingredients is known, then it may be advantageous to base the sterilization process on this organism. Figure 5.5 illustrates the effect of increasing medium sterilization on the yield of product of subsequent fermentations. The initial rise in yield is due to some components of the medium made more available to the process microorganism by the cooking effect of a brief sterilization period. Richards, 1966. During sterilization, the nutrient value of the medium decreases due to following reactions. 1. Interactions between nutrient components of the medium. 2. Miller-type browning reaction leads to discoloration of the medium, as well as deterioration of nutrient value, caused by the reaction of carbonyl groups and amino groups from reducing sugars, amino acids, and proteins respectively. 3. Degradation of heat-labeled components. Certain vitamins, amino acids, and proteins may be degraded during a steam sterilization regime. Thus, heat-labeled compounds can be sterilized by filtration. However, for the vast majority of fermentations, these problems may be resolved by the judicious choice of steam sterilization regime. The activation energy for thermal destruction of Bacillus staphylococcus spores is more than for thermal destruction of nutrient. Thus, it would be advantageous to employ high temperature for shorter period to achieve desired probability of sterility, yet causing minimum degradation of nutrients. Batch sterilization is not possible, as high temperature cannot be kept for short period by this method. Thus, only solution to this problem is continuous stream sterilization. Now del factor equals natural logarithm n 0/n t, but from above equation natural logarithm n 0/n t equals a t e raised to minus c /RT. Thus, del factor equals a t e raised to minus c /RT. On rearranging equation, natural logarithm t equals the advantages of batch sterilization over continuous sterilization. 1. Lesser assets apparatus expenditure. 2. Less chance of contamination. Processes require the aseptic inoculum's transfer of the sterile broth to the sterile vessel. 3. Easier manual control. 4. Easier to use with media having a high amount of solid material. The design of batch sterilization processes. The main aim of batch sterilization process is still to attain the necessary chance of getting sterility, with the least change in nutrient value of the medium. Continuous sterilization process is better than batch sterilization process in avoiding the damage of nutrients than a continuous sterilization process. The maximum temperature, which is possible in batch sterilization, is 121 degrees Celsius. Therefore, the method adopted, so that medium exposed to this high temperature, for a short period, high temperature, and short time sterilization attained by taking into consideration the heating and cooling time of the batch sterilization. The Interfer and Humphrey 1959 offered a method to evaluate a role of heating and cooling periods in sterilization process. The following points should take into consideration for a batch sterilization process. 1. How much temperature of the fermentation medium is increased during heating or decreased during cooling periods of the batch sterilization. 2. The initial number of microorganisms in the medium. 3. The thermal death rate of the selected organism. Requisite del factor is designed by knowing the initial number of organisms in the medium and the danger of contamination. Commonly accepted threat of contamination is 1 in 1,000, which means number of living organisms after time, t is 0.001. However, the killing of cells takes place during both the heating period and cooling period of the sterilization process, in addition to during holding period at 121 degrees Celsius. Regardless of the volume of the batch, the minimum number of organisms to contaminate the batch is 1. On integration of equation 1, the following expression is obtained. Nt/m0 equals e raised to minus kt, Equation 2. Where M0 is the number of viable organisms present initially, MT is the number of viable organisms present after a period treatment T, on taking natural logarithms. Equation 2 reduced to natural logarithm n T slash n 0 equals minus k T. Equation 3. Therefore, k T equals natural logarithm n 0 slash n T. Equation 4. Advantages of a separate, medium sterilization vessel. The medium sterilized in a cooker, in a more concentrated form than would be used in the fermentation, and then diluted in the fermenter, with sterile water prior to inoculation. This would allow the construction of smaller cookers. One cooker may be used to serve several fermenters, and the medium may be sterilized as the fermenters are being cleaned, and prepared for the next fermentation, thus saving time between fermentations. In some fermentation, the medium is at its most viscous during sterilization, and the power requirements for increased agitation lessened by aeration. A fermenter equipped with a powerful motor would provide sterile medium for several fermenters. The fermenter spared the corrosion, which may occur with medium at high temperature. Disadvantages of a separate, medium sterilization vessel. The cost of constructing a batch medium sterilizer is much the same as that for the fermenter. If a cooker serves a large number of fermenters, complex pipe work would be necessary to transport the sterile medium, with the inherent dangers of contamination. Mechanical failure in the cooker, supplying medium to several fermenters would render all the fermenters temporarily jobless. The provision of contingency equipment may be prohibitively costly. Advantages of batch sterilization over continuous sterilization. 1. Lesser assets apparatus expenditure. 2. Less chance of contamination. Processes require the aseptic inoculum's transfer of the sterile brought to the sterile vessel. 3. Easier manual control. 4. Easier to use with media having a high amount of solid material. There are two types of continuous sterilizers. 1. The indirect heat exchanger. 2. The direct heat exchanger steam injector. Indirect heat exchanger, double spiral type. Indirect heat exchanger, double spiral type. The most appropriate indirect heat exchanger is double spiral type, consists of two sheets of high-grade stainless steel. They are molded around central axis, in such a way that they form a double spiral, as shown in Figure 5.8. Steam and medium pass through two different plates, in opposite direction, to obtain sterilization temperature. This sterilizer is also used for cooling of the medium, after proper holding time. Incoming unsterile medium is partially heated, which itself is a cooling agent for medium, which is there in the sterilizer. The major advantages of the spiral heat exchanger are: A. There is less chances of contamination between medium and liquid used for cooling, or steam, as they are separately moving in a compartment formed by stainless steel plates with gasket seals at the end of the plates. The exchanger will be cleaned by the steam, or the liquid used for cooling, and continues movement of the media, so that there is less chances of sedimentation, fouling, and burning on. Alternate plates of heat exchanger allow two different liquid or steam to circulate through them in opposite direction. Two plates divided by gasket. Problem with this gasket can lead to cross-contamination of various streams. This sterilizer is useful for completely soluble media, as any suspended solids can block the plates. The stability of this sterilizer increases by adding extra plates to it. Direct heat exchanger. Figure 5.10. Continuous sterilization system. Direct steam injection. Indirect heat exchanger. Medium heated with the help of steam, and cooled by sudden expansion of the medium, in vacuum compartment. Cooling happens almost instantaneously. Figure 5.11. The continuous sterilization system. Spiral heat exchangers is shown above. Hot water passes through system for the sterilization of the plant, before sterilization of the medium. Steam used to sterilize pipework and fermenter. Heat is conserved by using incoming media, which will cool sterile medium, which in turn get preheated before reaching the sterilizer. Advantages of continuous steam injector. 1. Very short heating up time. 2. It may be used for media containing suspended solids. 3. Low capital cost. 4. Easy cleaning and maintenance. 5. High steam utilization efficiency. Disadvantages of continuous steam injector. 1. Foaming may occur during heating. 2. Direct contact of medium with steam required, that allowance be made for condensate dilution, and require clean steam, free from anti-corrosion additives.